So now what I'm going to show you is this. I'm going to sample this over and over again. Okay, so in other words, suppose I have my detector, send out, I read a signal, and I keep reading 30-second slices of time. Okay? And presumably, I keep getting different noise every time, right? Because it's white noise. So what I'm going to do is ask, what happens to these if I go through and I start sampling over and over again? Okay? I can do anything I want. I am master of my code. I can make noise a million. And by the way, that might just be one realization. If I run it again. Okay, so there's a little bit of a spike there. Fine. Go 30. I want to try to clean that up. As far as you can see in that blue, there's no evidence of anything. Right? But remember, you got to launch a missile or do something cool like that, or save your dog. So you got to figure this out. Don't want any dead dogs in this class because I'll be held accountable probably. All right, so here's what we're going to do. We're going to do a little loop for j equals 1 to 30. So what I'm going to do in this loop is the following. I'm going to take my deal here. Actually, this just needs to be defined once, so let's bring this outside loop. So I have some noise, which is 30. And let me take away these subplotting routines for a moment. Okay, here's what I want to do in this loop. I'm going to go in this loop 30 times, and each time I do it, I'm going to generate a new signal. Sorry, I have the same signal, but I'm going to generate a new signal because I'm going to add different noise to it. So it's the same signal that I keep reading, right? So in a radar problem, if there's a plane out there, I keep picking up that signal from the plane, but it's buried inside noise, which keeps changing in time. Okay, so every time I do this, I have this U of t which stays the same, but now the noise changes every time. So every time I do this, I get different noise on it, different noise on it. So each one of them just looks just like what we had before, nothing there. So what I'm going to do is I'm going to just keep doing this, and I'm going to ask, if I do this, and I go through this loop, I want to actually just calculate the average of what my spectrum looks like. I'm going to add, if I take 30 measurements, I'm going to add them together, divide by 30. What happens to the noise? What I know is, if it's white noise, and it's uncorrelated, all that noise should have mean. Sweet. Who thinks it's going to disappear? Anybody? 1. Whew. Tough crowd. Tough crowd. All right. I'm going to show you a magic trick. Okay. All right. Laptops usually don't come out of your sleeves. iPhones can. But, okay. One believer in the class. Let's see how many others I can make believe in this. All right. So here we go. What's that? Inverse Fourier transform. So let's go through this and say, okay, here's what I'm going to do. I've got to keep track of all this, right? So what I'm going to do is the following. I'm going to make a vector called average. And I'm going to start off with just a bunch of zeros in it. And what I'm going to do with this vector is, after I've computed this signal, I'll say, well, my average is what it was before plus this UTN. So just keep stacking the information in it. And at the very end, after I've done this 30 times, so I'm going to go through this loop 30 times, keep stacking my average information there. And at the end, I'm just going to take this signal and divide by the total number of times I did this, right? So I could say, all right, well, how about we do this? Av is equal to absolute value of. So first, I'm going to shift it. I took 30 slices, so I'll just divide by 30. We'll make this a little more general in a minute. Actually, let's do the following. So we took 30 realizations. Usually, I don't like to make variable names that long because I misspell them if they're that long. So what I'm going to do is I'm going to take I'm going to basically, remember av is basically, I've added it all together. By the way, you don't add the absolute value. Okay? It's not like you take the absolute value of each and add them together. You take the raw signal. Otherwise, the minus and pluses that are there don't cancel. It's all positive, and it all adds up, and then it'll look like, no, it's worse if you take more beta. Right? It should always be better. You sample 30 times, you got 30 things now to make a decision with. Right? Okay. So I add them all together. I'm going to FFT shift it, take its absolute value, divide by realization, and I want to plot that. Okay? So let's go ahead and plot it. All right. So here's what I'm going to plot in here. First, the original signal. The absolute value. Oops. So this is my perfect signal. We'll plot that in red. So remember what I did is before I polluted this thing with noise, I had this, I know what the answer is supposed to be, right? And I've added noise to it. So this is what the answer is supposed to be. That red line is going to come out. Okay? Now, let's look at this compared to the average, which is I added everything up, divided by the total number of realizations, and I'm going to plot that in black. Okay, and go. Okay. And, by the way, let me plot a single realization. If we go through this loop, we went through this loop from j equals 1 to realizations. The last time we went through the loop, we had this thing called UTN. So that was just one example realization. Let's also plot that. So KS versus the absolute value of, and FFT shift of UTN, there. And we'll plot that in yellow. I want it to be sort of subtle. Okay, how about cyan? Okay, I want it to be sort of not a strong dominant color, or else it'll take up the whole picture. Okay, so first of all, so let's talk about this picture. The cyan is one measurement. My last one. I took 30. That's what the cyan is. The red is the exact answer. And the black, that's averaged over 30. Okay? Actually does not so bad. Look at that. It kind of gets my peak right. Let's see how well we can do. So, right? So, in fact, here's what we're going to do. We're going to start looking at realizations. What happens if I have one realization? I get the blue. If I have two, how well do I do? You know, and then we'll start stepping it up to see how well does this converge. Okay. What's the answer if I have 1,000 a million? Okay. What's the answer if I have 1,000? Infinity. Sorry, that's the word I was looking for. My daughters, they're 9 and 6, and they're trying to understand this thing called infinity. They've heard of it. Like my youngest daughter, 6, is like, what happens if you? And she always makes up these toy problems, like 10 billion 35. Is that bigger than infinity? No, you got to go bigger. What happens, though, if you multiply that plus 20? The older one kind of gets it maybe a little bit. The younger one, she's there, getting in concept of infinity. And if you go to infinity, that red line will be black. The black line will go right to the red line. And you had a question. No. Yes. Okay. Yes.
Why don't you need to FFT shift to average?
Oh,
we did already.
I did.
You did it when you averaged.
Yeah. I shifted it when I averaged. So now let's look at this thing here. And in fact, you know what? This is going to be pretty sweet. We're going to make a little movie. Ready? You're clearly not. But anyway, okay. All right. Let's try to do this. Let's put this inside the loop, and we'll plot it inside the loop. So when j is 1, it's going to plot this. Hold. So then we're going to do this. Pause for half a second. And so when it goes through the first time, you'll see, in fact, what we're going to do is take out the cyan line. That's the individual run. And all we're going to plot is essentially the average versus what we're supposed to get. Ready? Okay, let's see. J. Thanks. Boom. Good? Anywhere else? I think that hopefully is it. And now we're going to go also through and do this 100 times. Oh, yeah, that's not a good idea either, right? Hold on, hold on. Oh, so I should call this something else. How about that? I faked my code out. Thank you. Av2. Okay? We're ready? I think we're ready to push the go button. It will. Hold on. Here we go. I got to pull this in so you can see it. Oh, come on, come on. No, okay, now I got to kill it. Okay. There it is. Okay, fine. It's going through. See that? See what's happening? Dang. I know. What's it looking like it's doing to you? Okay. It's looking pretty good to me. Is it looking pretty good to you? I don't know what realization we're on. And what you could see, as we take more and more realizations, right, and we take more and more averages, we keep sampling this thing out, the noise cancels itself out. And you basically get the black line is just folding right onto the red, what it's supposed to. There's a real signal in there. Okay? Now, if there was no signal in there, it would just all go to 0. Okay? So this is another way to take your data. Subtract the noise out. You know something about noise. Make use of it. If there's anything in the problem that you're not making use of, you're probably not doing the problem right. Okay? Every piece of information you have should be used. Here, we're using information now about the noise. Okay, after 100, this is what you get. So, this can be like your dog problem. Your dog problem is the following, right? You're going to, first of all, I haven't told you what the center frequency is of your dog problem. Here, I kind of knew. I embedded, I have the answer, right? So on my computer, I said, make a little signal right there in the middle of your domain. I don't do that with the dog problem. I make it up, and I don't tell you where it is. So you got to figure out where I should even filter, right? All right, so in this process, you notice that if I sample a lot, I clearly have a spike right there. So even if I didn't know where to filter, I'd say, oh, maybe I should filter right around here. There seems to be something there that's not just noise. We got that?